I'm going to talk to you today about work that I have done recently in trying to design machine learning processes for more equitable health systems. And the way that I want to anchor this talk is saying that in general, I believe that we need more and more diverse data. And I call the data that we work with in health spaces embodied data because this is data from human bodies. So we need to be very respectful of it, which I think this is not the audience I need to say that to. But in general, if we want to design robust, private, and fair algorithms, we're going to need more diverse data for research use because we don't just want to replicate the current medical harm that's being done to different subcommunities. We would like AI to improve science and address medical harm, and that requires newer, better, more robust data. So my lab does healthy machine learning. That's creating actionable insights in human health. I'm going to talk to you today about some of the work we do on the more technical side of how to improve models algorithmically, and then also how we audit healthcare systems with standard, no new machine learning required, just try to use state-of-the-art machine learning to audit what's happening right now. And then finally, how we can think about systems being deployed to actually benefit patients in the end. So because this is a mixed group, I'm going to quickly go through the standard way that most of the machine learning for health papers, I would say a vast majority, tend to be done. And I'll use one of my papers briefly as an example and then give you some highlights of others. Let's say that there's a patient like Sumana and she's having trouble breathing. The way that these are usually set up as a standard in the machine learning for health community is we observe some patient data as a time series. This happens to be ICU data, intensive care unit data. And so we'll observe data that looks like this. Maybe it's noisy, maybe it's irregularly sampled in some cases. We might do some things to fix that or address it or drop patients that have certain lack of certain data or other constraints, which those are all questionable decisions, but we make them. And then we play a game where we try to do real-time prediction of something that actually happened to this person, right? So we're not deploying these things all over the place. We're actually just taking a bunch of retrospective data, and then we're pretending like the model that we're training gets to see this data in real time. And the way that we penalize the model is by scoring it poorly when it doesn't predict a thing that actually happened, like the patient gets a drug, the patient dies, the patient develops some condition. And usually we have some sort of gap time before the actual thing occurred because of the way that data labels can propagate backwards in healthcare records. So here's an example. We tried to predict clinical interventions in intensive care units. We took over 30,000 patients worth of data. We combined static variables, time-varying vitals and labs. These are things like oxygen saturation, lactate levels. There's a common way of, it's common now, of pre-processing clinical notes so that those two are included in the record as a vector of numbers. So all of the parts of your record, of your electronic healthcare record data, get processed into a matrix of numbers. And now we can represent all the patients in a hospital as a large tensor of numbers. And this is usually where machine learning people in health sort of play, right? We are given this set of pre-processing steps, and now we have a vector for every person or a matrix for every person, and so we have a tensor for all our patients, and we train models. And you can do really impressive things with these models. So this is a paper from several years ago now when I was a PhD student, and we showed that if you use deep neural networks and think sort of intelligently about the representation, you can get very nice performance results, high AUCs at predicting a range of interventions that might be important in the intensive care unit. So here that's ventilation, non-invasive ventilation, vasopressor drugs, fluid boluses, that's all great. But it's not just me who does stuff like this. I want to emphasize there's a whole community of people. This is a table from one of Eric Topol's paper, and you've heard from two people just before me who are in this community as well. There's a huge group of people who develop machine learning models for a range of prediction tasks across the human lifespan. But the thing that I want to focus for a minute on in this table are two things, right? In this community, in my sub-community, we tend to report our AUC as one number, one average number across all the subjects we have. And then our sample size can vary pretty widely, right? So our goal, I should say, these are all models that performed at or above the humans they were benchmarked against, which is why they were included in this table. But the concern is, if this is learning from real data, as we've heard from many other speakers over the course of this workshop, what exactly is it going to learn? And is that something that I want a machine learning model to replicate and enforce in future deployments? Because doctors don't always practice in a way that we would want all future doctors to practice. So I'm going to talk a little bit about some of the auditing work that we've done in machine learning systems, because a patient might want to ask that question: will this model work for a patient like me? And so here's an example of something that's very popular. There are dozens per week of papers that are written not just in the machine learning for health community, but within the imaging sub-community, which has its own academic conference even, where you take very large medical imaging data sets. So in this case, we did that as well. We took 3 very large publicly available chest x-ray data sets. That's over 700,000 images of chests. And we trained a DenseNet, a kind of convolutional neural network, state of the art, predicts as well as everybody else, benchmark in the paper, it's all great. But we trained it to predict one of the labels that's present called no finding, which means the model says the patient is healthy. So this is one of those things that could happen in a triage situation, which is indeed what models like this are often proposed for when the FDA tries to clear them. We're going to use this for triage, so somebody will come in, it's COVID times, our ward is very busy, the emerge is crazy, we took a chest x-ray, we need to know who to prioritize and who to send home. This person has no finding, they're healthy, they're fine. And then we're going to measure the false positive rate in different subpopulations. And we're going to call that the underdiagnosis rate. Because if you falsely, positively say that somebody is healthy, that means that that person's actually not healthy, there's something wrong with them, and the model incorrectly said, send them home, they'll be fine. And if you deployed a model that had a higher model underdiagnosis rate on one subpopulation, like female patients, it would lead to a higher rate of no treatment for patients who actually need it. So we trained and optimized the model, and we find that these state-of-the-art chest x-ray diagnostic models have the largest underdiagnosis rate in female patients, young patients, Black patients, and patients on Medicaid insurance. And the intersectional identities are more underdiagnosed than the aggregated group. And so we find that Black or Hispanic female patients are underdiagnosed more than female patients, and more than white female patients, the majority group within that subclass. One of the responders, the reviewers to that paper, which was published in Nature Medicine last year, yes, it was last year, said, this is a very simple point you're making. Why don't you just say that we should audit the fairness and predictive models? And we said, well, we did say that in the paper. But this is not something that is new, I should emphasize. I think we were the first to do it in the chest x-rays. But this is a paper that I wrote at the end of my PhD with other colleagues, where we did, in fact, do this audit in machine learning models that were trained on ICU and psychiatric data. And we found that there was, in fact, variation by insurance type, by self-described race, and by self-described gender. And so this is something that we could just recommend generally. We want models to be audited by subgroup. FDA, before you clear a model to be released in a medical setting, we want things audited along certain subclasses. But the problem is, as we have incredibly complex data, human data that we're training on, that is generated from a biased care system, we could learn things that would be very hard to audit and remove. You've all probably heard of contextual language models. These are things like BERT models, GPT-2, GPT-3. These are language models that are trained on vast amounts of human language text. And then they're used now in many settings, but health is one of the settings they are used in, to generate text, to fill in medical notes, to provide chatbots, to suggest triage recommendations, you name it, they've been proposed for it. and in fact deployed in one case in the NHS, Babylon Health, to provide advice to doctors. So here's an example of a prompt from a real medical note in a Boston area hospital. Blank patient became belligerent and violent, sent to. So I'm going to fill in race, and then I'm going to ask the model. This is the CyBERT model, which is publicly available. You can download it now. And it's trained on PubMed. It's not trained on 4chan or Reddit. It's trained on PubMed, scientific articles, okay? So if I say a Caucasian patient or a white patient became belligerent and violent, CyBERT completes the note for this patient with they were sent to the hospital. But if I say an African, African-American, or black patient became belligerent and violent, CyBERT completes their note with they were sent to prison. This is really problematic because this kind of biases are also not something that we can say we will fix downstream. So somebody asked me last year, okay, you've pointed out that representations that we trained on biased data. For example, there was a really good paper, I think, by DeepMind, where they trained a acute kidney injury predictor on VA data. But VA data is 6% female. And so I was asked on a panel, well, why can't we just, none of us can touch VA data. It's very hard to get access to. Why can't we just freeze that representation and then try to balance later downstream when we have better data, right? And so we actually ran that experiment because I didn't know the answer to the question. And we found that if you learn a representation, a latent space, an embedding, some sort of representation of data that is biased, and then you throw that biased data away, and then you bring in fair, balanced data to train and test your model on. If you map this balanced data onto the old biased embedding, then you have the same gaps in downstream tasks. So this is not something where we can say, well, we'll just do, wherever we can now, and eventually this problem will be solved. This is an issue that when you learn representations with biased data, the representations themselves cannot predict. They never learned the feature space, the representation space. They were never rewarded for or penalized for these variations in different subgroup performance. And you might say, okay, that's one example, but this is clinical data. How deep could that go? And I will say I have been surprised at how deeply bias is embedded in the clinical landscape. There's lots of very, very good research on this from a social science and epidemiological perspective. But here's a pop quiz. Do you all think that this note is for a black patient or a white patient? It's a real note. And it had race mentioned, and I redacted it, okay? And then don't feel bad if you don't know, because I'm not just pop quizzing you. I actually pop quizzed a bunch of doctors on this, and they can't tell. So when you redact a patient's race from medical notes, clinicians are really bad at determining the race of the person in the note. They essentially guess, and they usually guess white. But models, even very simple models, are actually really good at predicting the race of a patient from a race-redacted note. And some of the things they use maybe might make sense. In the Boston population that goes to the specific set of hospitals, there are more patients with dialysis and hypertension or African American. And this is all self-reported race, not genetic ancestry. So we find that it's possible to predict race from a clinical note even after you strip out the direct indicators on two different data sets, the mimic notes from Boston and the Columbia notes from New York, at a very high level, even when you use really simple models. And it gets better as you use slightly more complicated models. The most predictive features come from some categories that make sense, right? So patient conditions, there's a correlation with comorbidities. And some of them are things that are not meaningful comorbidities, but just biases in the healthcare system. Like doctors and clinical staff in general do not make references to darker patients' skin. And this is well noted in the dermatological literature, where only 14% of the images that are in medical textbooks and case notes are on darker skin anyway, causing a huge amount of underdiagnosis of conditions that have skin-related presentation. But just the fact that you said something about the patient's skin means to the model that this must be a light-skinned patient who probably self-reported their race as white, because it's learned that doctors, clinical staff don't talk about darker skin and clinical presentation of symptoms in scan. We also found weirder things, like slightly more problematic even than that, such as the word difficult is used disproportionately more to describe black patients than white patients, and really bizarre things, like amongst married female patients, we're much more likely to use the word husband somewhere in the note, for example, talking about care directives or planning for the patient for white married female patients than black married female patients, which is something when we talked to care staff, they said tends to happen when they have very difficult engagements with patient families where they are not having a good relationship with the patient's family. That's reflected in the note. And so this is something that the model is picking up on. Here's a second pop quiz, which is maybe more disturbing, because in that previous example, I could tell you, okay, well, you know, the care staff has unconscious biases, or there's different things that are happening, and that shows up in the notes in these really subtle ways that a human can't tell, but a model can. But what about this? This is just a chest x-ray. Is this patient black? Can you tell? Radiologists can't. We also tested radiologists for this too. This has been my new favorite pastime, calling all the clinicians I know and making them take exams. It's trivially easy for AI models to detect a patient's self-reported race from medical imaging. This is across many sites. We didn't believe the result at first, and so we replicated it many, many times. We also looked at international data sets. We called up collaborators in Australia to try to figure out if there was other things going on. We looked at data sets where it was a balanced distribution of patients. So we have a collaborator at Emory in Atlanta, and half of the patients that they see are African American and half are white. These results hold across many subsections. And you might say, well, you just told me that there's all of these proxies in the representations. There's information that's leaking about who you are based on comorbidities, based on how the staff is treating you. And so we actually told the radiologist, can you just brainstorm the top 10 things that you think the model is using to cheat? And then we evaluated them. It's not body mass index, it's not breast density, it's not bone density, it's not disease distribution. We also tested a bunch of other things. It's not high or low pass information exclusively in the frequency domain. In fact, if you band pass filter, meaning you only select very specific short frequency ranges, these images, you can still see very, very high performance of models, even when the chest x-ray image itself doesn't really look that much like a chest x-ray anymore. I'll tell you what our theory is. We can't prove this because we don't have actual photos of patients. Our theory is this is probably melanin. It's probably that the imaging is calibrated in to white test dummies, as the way that cameras were or still are in many cases. And melanin is impacting the bounce back from a medical physics perspective in a way that is picked up because of the narrow calibration range. Why is this problematic? It's not by itself. It doesn't really matter that the model can tell your self-reported race. What matters is that it can do it perfectly when humans can't at all. They just can't. And so if a model is perfectly wrong on black patients, a radiologist wouldn't know. Oh, Cynthia, go ahead.
Oh, just a 2-minute warning.
Okay, good. So the last couple of things I want to talk about are, can we fix things easily? So can we fix models with explanations? And this is a widely proposed way of addressing issues. So we looked at 2 very popular kinds of model explanations. So these would be local and global ones like Lyman Shop or sparse decision trees, generalized additive models. And we wanted to measure the fairness of models once they had been explained. And so we looked both at average and worst case fidelity differences and the average absolute difference in fidelity. And we didn't just look at health data sets, which is my usual thing, and variation across sex. We also looked at several other pretty standard data sets that are used in the explanation and fairness community. And we found that across the board, there are larger subgroup fidelity gaps. The explanations make the model worse, for example, for women in the health data set. And that the gap gets worse the more you explain it, the smaller dimensional you make the explanation be. And this is because, again, your group can be detected from your representation. And so it's impossible to remove all of this proxy data from the information that's gathered from the healthcare system. So the last thing I want to talk about briefly is, what are we supposed to do with this? One safe way we could imagine planning interventions is by including constraints. And I'm going to use checklists as an example because they're easy to use and deploy and verify. And the problem with them is when you make a medical checklist, right now you get a bunch of experts together and they have to have a discussion. And then it takes a long time, and then in the end, you still have these checklists or risk scores that, in this great paper by Vyas et al., over or underestimate risk for African American patients when you include race as part of the checklist. And so we decided to try learning optimal predictive checklists, where you say, I want to directly try to optimize the checklist that should predict this thing at the highest accuracy possible. But we also wanted to be able to include fairness constraints, because let's say we're trying to predict something like mortality after getting a treatment like CRRT in the ICU. We don't want it to falsely positively predict you'll die more often for Black women than white men, because then those people would be denied treatment. And so when we run the checklist without fairness constraints, this is the checklist that we get. It's not using race, it's not using gender. There are no obvious proxies like weight or height for gender, for example. There's no obvious proxies for race like hematocrit level differences, which some people have reported from lab values for African American patients. And yet this model, this checklist, has a max false positive rate gap of over 50% between Black women and white men. It's not obvious what the proxies are, but again, it's so deeply embedded. The spurious correlations are so deeply embedded in the health data that you have to add fairness constraints in order to perform well, because otherwise it just learns something that is exhaust of an unfair process. And then we have other work that I won't discuss about how we safely give advice, trying to look at what happens when you give information to clinicians with different caveats and then see how they react to that. I think this is an understudied field in general, and there should be a lot more effort, not just in how we make models that are fairer, more safe, more reliable from bad healthcare data, spurious healthcare data, but then once you have a model that's going to do the best that it can, how do you deploy that in as safe a way as possible? Thank you.